right, welcome back from lunch. Let's go ahead and get started with our next presenter from Alastair, Basden.
Thank you. So I'm Alastair Basden from Durham University and also part of DRAC. And I'm going to tell you today a little bit of work that we've been doing in composable infrastructure and some of the struggles that we've had with that. So first of all, what is DRAC? Well, DRAC is it's a UK national HPC service for one particular research council, STFC, Science Technology Facilities Council. So DRAC is a tier 1 HPC facility. At times, it's the largest provider of UK compute, certainly for academic research. It's got 4 sites based in Edinburgh, Leicester here, and Cambridge. It's got the data intensive system and the memory intensive service at Durham, where we concentrate on high memory workloads. So what we have within DRAC is kind of bespoke systems for the associated science that they're trying to do. And we find that's more cost effective than having a single system that tries to do everything. And it really means that we can push the boundaries of what we try and achieve. So in Durham we have the memory intensive service COSMA, cosmology machine. There are 2 generations of COSMA running at the moment. We've got COSMA 7, which was installed in 2018, and then our newer system COSMA 8, which is about 70,000 compute cores and 15 petabytes of storage, and that's kind of our go-to system that most users are using at the moment. So the sorts of science that we do on COSMA is anything really that within STFC that involves high memory workloads. And the prime example there is simulation of the universe. If you're trying to fit your universe into a computer, you obviously need a lot of memory to do that. When it will never have enough, I can safely say, we'll never have enough memory to simulate what we're trying to simulate. But we also do things like nuclear physics, there's particle physics going there, black hole mergers, things like that, planetary collisions, and galaxy formation. So a lot of different science, mostly to do with stuff out there, goes on COSMA. Okay, so moving on to the point of this talk, composability. Well, first of all, what is composability? If you have a spell checker on and it's automatically correcting stuff, you end up with compostability. That's not the purpose of it'd be good to have computers that could do that, wouldn't it? But it's not what we're aiming for here. But composability is separation of device resources. So when you're talking about compute or accelerators, storage, network and RAM, you're treating those as a service. The physical components are no longer in a server, but you're able to, at a click of a button, join them together and basically create a server upon demand. So you're building your compute capacity as you require it. Which then means that your clusters can be better matched to typical use cases. So if you've got a particular job that starts and it needs so much memory and so many GPUs, that can then be composed together and provided with a system to do that. So where could this be useful? Well, I think when people talk about composability, the first example that people usually think of is massive GPU systems. So if you want tens of GPUs in a server, you can't really do that in a physical server. And so you have to use composable infrastructure to do that. And that's for workloads that really just need a lot of GPU compute, and any CPUs that you add are just wasted. So really that's the first instance. The second example is where you've got scarce resource sharing. So, for example, if you were to buy a new cluster and you kit all the nodes out with GPUs, but a lot of your workloads aren't suited to GPUs, where you end up most of the time with a stranded resource and you're wasting those GPUs. So instead what you can do is you can have a subset of GPUs that can then be assigned to nodes by the jobs themselves. When they start, they can say, I need 10 nodes and I want each of them to have GPUs. You look around, are those GPUs available? You build your cluster with those, click of a button or whatever, or Slurm does it for you, and goes away, and you've got that. And then the rest of your cluster is maybe CPU only, and you're not then wasting those GPUs. And another reason you could look at composability is for memory bursting, so adding RAM to servers as required. This is where maybe your average workload might use 1 terabyte of RAM, but you might have some workloads that need a lot more than that. And rather than kit all your servers out or a subset of your servers out, you just have a big bank of RAM that you can attach to these servers on demand and go away and start using. And finally, networking. I haven't really thought this one through very much, but I'm sure there is a very interesting case that could be made for composing multiple data processing units, Bluefield, something like that, GPU cards combined with them, composing all that into a server. But that's not quite sure what that would be yet. So on Cosma, we have a very small composable test bed. We use a liquid fabric, and basically what we have is one, it's a very simple system, very small scale system at the moment. We just kind of look at this. We've got one OSS chassis, which inside it has 3 GPUs and 4 RAM cards that are providing 12 terabytes of RAM between them. There's a PCIe switch and controller, which again is part of the liquid solution. And we have four of our servers, 1 login node and three other nodes that have fabric cards in that we can then compose these infrastructure to. And this kind of black box on the side is basically, and you're not supposed to see it, but it's a screenshot of what the different PCI bridges look like in the system with all the different memory attached, and there's GPUs somewhere there and things like that. It's a little bit confusing to me, but anyway, it seems to know what it's doing with it. So for our GPU system, we have these 3 GPUs. We can assign them to 4 servers. So this is again an instance of where we've got more servers than GPUs. They can be hot swapped. Occasionally, we find that decomposing a GPU from a server causes the server problems, I guess depending on what it's been doing. The way we run it actually is usually static. So what we normally do is we just have a GPU assigned to 2 of the servers plus the login node, and that's generally the way we run it, unless someone comes along and says, actually, I would like to have multiple GPUs in a server or something like that, and then we'll recompose a system for them. It is possible to integrate all this with Slurm so that they can request that resource in their job and have it composed automatically. That's not something we do. Not something we've even tested. It strikes me as something that's a bit high risk and has potential to go wrong at the moment. It's all a bit kind of Wild West, if you like. Now, one thing that this has is the servers there, each of the servers you can see there, each has a PCI 4-lane connector. Okay, so that's the first bottleneck you have in the system. Whereas the GPU cards are obviously 16-lane, the connections to the fabric are only 4 lanes. So you're already limiting your bandwidth by a quarter. Of course, if you're doing workloads where you've just got some data to put on a GPU, which isn't a huge amount and it's doing a lot of processing, that doesn't matter. Within the GPU chassis, there are 3 GPUs, but there are 2 fabric cards. So 2 of those GPUs sit on 1 fabric card. So again, that's more of the bandwidth sharing. The other thing to point out about this system is connectivity is a bit of a pain per card. For some reason, you've got 4 SAS type cables. They're a bit horrible. They sometimes you have to, particularly when you're setting it up, you can have problems. They can have to replug them and that sort of thing. So, as it stands, it's a solution that works, but it's not something really at the moment I would want to have on any sort of scale. For our composable RAM system, we have 4, well, they call them Honey Badger cards. Again, these are PCIe cards, and they've got basically Optane drives sitting on them. Each card has 8 Optane drives, 360 gigabytes each, so about 12 terabytes of RAM in total. Now, each of those drives can be assigned individually to any of the servers. And by default, we basically split them equally between the 4 servers. So that's 8 drives per server, which gives us about 2.5 terabytes. The maths don't quite add up, so there's something gets lost somewhere in the composing. But anyway, about 2.5 terabytes extra per server of what it has natively. There's a company called MemVerge who have some software that we use that maps those Optane drives into RAM, and it does some quite clever stuff under the hood. It's basically doing tiering, so hot data it moves into RAM, warm data it moves off into the larger Optane tier. It is in this case a bit of a pain to recompose it. If you want to take RAM away from the server, generally speaking the servers don't like that, and if you want to add RAM, again basically it involves a reboot of the server to recompose it and then run some scripts to bring those drives into the right sort of state. But it does work, and it is, you can create a server with as much RAM as you like without having to actually do anything physical. So it is kind of there in a way. We also, in production, this is all in production, and we are running one of our Jupyter hubs is running on the login node on this composable memory. So, it generally works. Users are using it without really even being aware that they're using it. Now, okay, the bandwidth, the memory bandwidth, of course, will be less because it's all going over these PCIe 4 lanes. But for the sort of workloads that people are doing in a Jupyter hub, that doesn't really matter. It just means they're chewing up less of the CPU and affecting less of the other people a bit less if they try and do something they shouldn't be doing. So that's what we have. One of the things that we're looking at as a potential for our next step in this journey, if you like, is a stereo system. So this is moving from the PCIe fabric, which is generally fairly small scale. You wouldn't want to extend it beyond a rack because of cable length and that sort of thing. What we're looking at now is a system that potentially can go much larger, can be a cluster scale fabric. And this is basically, it's a stereo, otherwise used to be known as Rockport. It's a flip-based fabric, so very small packet sizes that can be broken up and spread around all the fabric available to get from source to destination, that sort of thing. Generally speaking, well, the system we have, a Rockport system we have at the moment is a 6D Taurus. This newer system, it can do other topologies as well, but all sorts of flies for some reason. And can scale to thousands of nodes. And so we've already got some experience with using the Rockport Ethernet fabric, and so we think that this kind of composable fabric offers quite a bit of potential. Uses high density optical cables, standard MTP connections, so that's kind of a bonus there. And what with this system, what you have is you don't have a central switch, which is one of the drawbacks of, say, the liquid system. All the active components solely are in the server card. So in this diagram here, you've got the servers on the left-hand side. In the middle, they're all going to this box, which you might think is an active component. It's not. That's just pure optical, no power supply or anything like that. It's just optics being rerouted. And then it will go to a number of chassis on the right-hand side, which contain your GPUs or your memory or whatever else. And we're in the planning at the moment for an 8-node test system that we hope to bring up with some of this. So here we are, eight nodes. We're looking at fairly high spec CPUs in that. 200 gigabit connections into the server. So at the full PCIe 4 or half PCIe 5 bandwidth. A faster fabric transport to help manage any congestion that we'll see there. And in terms of what we put in physical hardware to be composed, we're at the moment just looking at GPUs. But one of the benefits of this sort of system is that later on, if we find we need more GPUs, we don't have to pull out servers and put them in the servers. We just install one more box with the GPUs in it, plug it into the fabric, and there we go. We've got some more GPUs that we can easily compose. Now, of course, coming along and actually just starting to arrive is CXL, Compute Express Link. And that is really designed to help with composability. And one of the things it brings is memory coherence. So you can start to do full composability of memory. You can do memory coherent I/O networking, which will give you very low latency communication, sub-microsecond, that sort of thing, where basically you can have shared memory regions which are shared not just between processors within a server, but shared between servers and cache coherent between them. And that's great because it then means you can get rid of some of your more traditional fabrics where your copy and send sort of things, where you've just got one copy. They can all work on the same data without copying, without shuffling, and that's great for something like cosmology. That's great. You can have all your particle data, all the models of the galaxies and so on, can be in one copy in memory, and the different servers can work on those aspects as they need to. So we think there's quite a lot of potential there. So it all sounds great. Actually, it's not quite so great. So if you're considering a composable system, some of the things that we've thought about that that are problems at the moment, certainly with the existing system. One is fabric reboots. You've got a single, with the switch-based solution, the PCIe switch, you've got a single point of failure. So if something goes wrong, you need to reboot your PCIe fabric, which means all the servers attached to that also get upset and need rebooting as well. So it's not great if you've got a system in production as we have. Now that will be mitigated once you've got a more distributed fabric doing that. Another thing that we find is that each server, as it comes within its BIOS, has a limited number of PCIe register slots. So that's actually, it's a number that's far greater than the number of slots that are physically on the system, but it's far fewer than actually we might want to compose. So when I said we've got these Honey Badger cards, 4 of them, each with eight drives on, that's 32 drives that we might like to compose into a single server. We can't actually do that because within the BIOS of these particular servers, they can't cope with that many PCIe devices. So, you know, although it would be nice to add 12 terabytes of RAM to a single system, we find actually in practice we can't do that. And the number that you can do depends very much on server model and type of server and that sort of thing. So perhaps in the future, the servers will be coming along with many more slots to help with this. Reliability can be a bit of a problem. It's certainly not a 6 nines of reliability there. We sometimes find that after rebooting a node, the GPU is no longer recognised, and that we think then needs a reboot of the fabric to help fix that problem. RAM as well. If you've got this RAM you compose, now generally you want RAM to be very reliable. And if you're connecting it over a PCIe fabric, it's going through the I/O bus, not the memory bus. It's going over all these lots of different SAS cables and so on. You get more errors on your RAM than you might like. The cost, it's not at the moment, because it's kind of all new and novel, it's not necessarily cheaper than just buying servers, each with the RAM and so on added in. I mean, one of the benefits is you can use cheaper RAM, which you can't actually fit in your server. But it's not, you could potentially have non-composable things at the moment that would work out cheaper or the same price. But I think along the line, the cost is going to go down. Particularly, it's not driven by HPC, but more driven by enterprise. And power usage. Now, this is an interesting one because these cards, you add GPUs, you compose a GPU. It looks to the server like that. The server thinks, well, that GPU is inside me. And then the server might, if you've got a few of them in, the server might think, well, my power supply isn't going to support all those GPUs. Even though it's not supporting them, the GPUs are powered by the chassis that they're in, the server BIOS thinks and starts complaining because it thinks it doesn't have enough power to drive them. So that's another problem, a hurdle that needs to be got over, which I'm sure will be got over at some point. It must be a fairly trivial thing. A custom firmware or something like that will probably fix it, but that's just something to think about. So if you're trying to compose a box with 40 GPUs in, it's just one thing to bear, it's a question that you might need to ask. Another thing that this system doesn't do particularly well is keeping track of infrastructure. If you know that one of your drives is dodgy, how do you work out which one it is? It's not in a particular server anymore, it's just somewhere in a box. If these things get automatically decomposed and recomposed, you then have keeping track of what the dodgy component, if it's only one that you suspect is dodgy, you then have to work out exactly where it is. It's not a dynamically recoverable system. If something goes wrong, it can mean that you have to reboot your whole fabric. And then, of course, one of the other downsides is the bandwidth hit you take by going through 4 lanes of PCIe, the latency hits and so on. So it is very much early days. But even in early days, I think it does have potential use cases. Net zero considerations, I think there's significant potential here. Primarily coming from lower embodied CO2, which actually is a significant fraction. Now that the UK national grid is starting to be decarbonised, embodied CO2, this is CO2 produced during manufacture, is becoming a larger and larger percentage of the system over its lifetime. So if you can have a composable system that has physically less hardware, you're obviously helping there. You're also better able to match supply to demand, so you've got less resource, less stranded resource, sitting idle, less GPUs, burning power, not being used. It's also expandable upon demand. This is, I think, one of the key things. So we could start off in the new system we're looking at, we might buy 8 GPUs, but if we find that people are really using those and want more, it's very easy to add more boxes, and they can then be composed to the servers as desired. So it's very easy to do that rather than having to change a whole cluster. So in conclusion here, I think composability works. It's a bit rough at the edges. I think we're not quite at the stage where you'd want to run a large production system based on it, but it's getting there, and it's 2 or 3 years away. We might start to see some of these in production as HPC systems. At the moment, there's a bit of lack of standards, and flexibility, as there can be a bit of vendor lock-in. That, I think, the situation there is improving, so we'll start to see some better stuff there. And yeah, I think another key takeaway actually is that these RAM-based fabrics, where you've got shared memory with CXL 3 point something or other, you start to see significant performance improvements for some code, particularly where they're doing lots of small data sharings between them. So that's could offer significant benefits for a lot of HPC codes there. So, thank you.